The Minimum Mars Ascent Vehicle is an aerospace engineering senior design project consisting of members Robert Asman, Jake Brazelton, Rikayla Ferguson, Amanda Fordyce, Kaylee Shevchik, and Cody Watson. Shown here is the Minimum Mars Ascent Vehicle poster detailing the process of designing, testing, and analyzing the results of the Balut system. The problem description outlines the questions and goals that the team aimed to accomplish during the testing phase of this project. The Materials and Methods section details the specific materials chosen to construct the deliverables, the methods of construction, and the methods of testing. The Results section provides an overview of the 3 major results obtained from wind tunnel testing, as well as additional results which aided this experimentation. In the Conclusion section, 2 abort sequence alternatives are provided which were derived from the results. Finally, the Supporting Materials section provides additional information which aids in any discussion of the project. The Mars Ascent Rendezvous System for Human Astronauts, or MARSHA, is a system designed to Theme 2 of the NASA Rascal Design Competition, the Minimum Mars Ascent Vehicle, or MAV. The constraints of Theme 2 state that the dry mass of the system must not exceed 5,000 kilograms, and the wet mass is limited to 20,000 kilograms. Additionally, the project is allotted $2 billion over the course of 10 years beginning in 2025. The primary objective of the mission is to safely transport a crew of 2 astronauts from the surface of Mars into a low Mars orbit, or LMO. The secondary goal involves ensuring the safety and integrity of Martian samples within a Sample Preservation Unit, or SPU. The collection of Martian samples enables not only a better understanding of planet composition and geological history, but also aids in the design of curated missions which ensures the safety of future inhabitants of Mars.
At 11.3 meters tall and 2.6 meters in diameter, MARSHA is a 2-stage vehicle and is fueled by a liquid oxygen methane bipropellant. Seen here is the concept of operations, demonstrating the general mission timeline through a series of critical mission events. The mission begins with engine ignition, followed shortly by a retraction of launch legs at 6 seconds and execution of the tip-over maneuver at 11.6 seconds. For the next couple of minutes, MARSHA will continue atmospheric flight. At 2.41 minutes and an altitude of 31.2 kilometers, MARSHA will execute stage separation and engine burnout. After injection into orbit, injection into transfer trajectory, and injection into parking trajectory, MARSHA will have achieved an altitude of 175 kilometers at roughly 16.71 minutes. MARSHA will continue orbiting until it is able to execute docking. After aligning with the Mars Rendezvous vehicle, MARSHA will dock and will rendezvous at just over 24 hours.
Moving back to the MARSHA vehicle, I'd like to speak about some of the subsystems that are integral to the mission. As mentioned earlier, the lower stage will be propelled by 3 Mira LM-10 engines, each providing 98 kilonewtons of thrust and each with a mass of 250 kilograms. We arrived at these engines after conducting a detailed trade study where we discovered the LM-10 engines produce a weight-to-thrust ratio better suited for our mission needs. The LM-10 engines are fed by fuel and oxidizer tanks situated on either side of the vehicle, as well as one in the middle, providing CH4 and LOX as the propellants. The fuel and oxidizer tanks are comprised of a lightweight, layered composite insulation, allowing for long-term storage viability. Transitioning to the structure side of the vehicle, the upper stage uses a highly innovative weight-saving carbon fiber isogrid structure, meant to provide the same integral strength as steel, but reduce the overall mass of the vehicle. The vehicle's skin will be constructed from aluminum lithium, which is resistant to corrosion that will be found in the Martian atmosphere. The vehicle will be sitting on 3 carbon fiber composite retractable landing legs, comparable to those found on the SpaceX Falcon 9. For determining the flight path, guidance, and abort situations, a single BAE Rad 750 onboard computer with a 2-core processor will be used. This computer selection is a legacy computer, meaning it has seen missions such as these before where they are proven to have worked in space environments. For rapid system response and decision making, the Rad 750 will use a VxWorks operating system. The guidance and control subsystem will utilize the same type of computer, but will be independent and decentralized. Should a system failure occur, it can serve as a backup command and control computer. Protecting both the astronauts and the MAV from the extreme temperatures of both Mars and space conditions was a high priority for the team. To complete this task, electric heaters and Joule Thomson cryocoolers were inserted into the crew cabin of the ship to maintain temperature integrity on the inside. A PICA heat shield was installed underneath the upper stage to protect the MAV in case of an abort situation.
Speaking of an abort scenario, throughout design development, the team stood by the belief that any manned ascent vehicle should have a system capable of returning itself safely back to its launch surface, and was the inspiration when transitioning to the hardware development phase of the project, leading to the primary objective to further develop and test an abort system that would decelerate the vehicle to a target speed of 7.6 meters per second or less upon surface impact. Historically, for a return to surface scenario, deployable drag devices are used. Selecting a large parachute on Mars was not favorable for decelerating from high supersonic speeds and presented a deployment concern operating in a much thinner atmosphere. It is hypothesized that a balloon deploying as a more structured body would be more reliable in achieving its desired configuration in a thin atmosphere, while offering a more effective design for the required deceleration. This is important since due to the mass constraints placed on this system, the team has proposed an initial size diameter ratio of 4:1 between the drag device and vehicle body. To evaluate the performance of the proposed balloon concept, a 3D printed prototype was fitted into the University of Arizona's Educational Wind Tunnel Test Section, which is of the dimensions 24 inches long, 12 inches wide, and 12 inches high, leading to a resulting size of a 4-inch diameter for the balloon prototype. Using a sting force balance to measure the actual force in small increments of increasing flow velocity, the drag coefficient was found from the prototype in this experiment and applied to an abort scenario.
When selecting an abort scenario, the altitude ranging from 0 to 32 kilometers was considered. From our trajectory calculations, the vehicle will separate from the lower stage at roughly 32 kilometers and enter into orbit. The point of interest selected to investigate for testing was 30 kilometers. At this point in time, the Reynolds number is 770,480, traveling at a Mach number of 3.36. Using the results from our experiment, we estimated a relative drag coefficient of 0.55 from analyzing the performance of the balloon. The terminal velocity was found as a function of altitude throughout the atmosphere, and it was concluded that a powered landing would be required for our MAV to slow down to 7.6 meters per second. To determine what specific burn should be completed and optimize the system would be dependent on outside parameters that were unable to be determined by the team. Several factors are known about the upper stage propulsion system, which allowed for its limitations to be established. As long as the system is falling below 3,100 meters per second, with a distance of 8,000 meters, the system may utilize its maximum burn time to land at the desired speed. The terminal velocity falls well within this regimen, leading to the conclusion that a successful landing may be achieved.